Okay, yeah, I might go back and just do it that one. I did see that, but I wanted to see if it's close.
Sorry, go back.
That's how I felt like I had to but then you wake up and you all right, let's get started. So what I got here is an activity, and as opposed to, I thought about it, pulling out the MacBooks, or the netbooks there, and they're not MacBooks, netbooks, and logging on to Maple, but that takes so long, and it's so slow even when you do get connected. I'm going to have you guys work on the first three, and we're just going to go over it together. That way you guys see how to work this thing, and you can, outside of class, do the rest of them, okay? So what you can do on them, though, is with each system, and we're just going to do like A and C together. For each system, I want you to find the eigenvalues of the coefficient matrix. And you can find the critical point as well. You might be able to find the critical point by looking at these ones. Critical points. If you set each of these equations equal to 0, what kind of shape would they graph to? Yeah, they're both linear in x and y. And there's no other constants. Negative 2x plus y equals 0. There's no constants, 3 or 5. So these would both be lines, right? Specifically, both lines that contain what point? The origin, right? If in standard form, negative 2x plus y equals 0, this is a line through the origin. It contains the origin because 0, 0 gives you 0. So the critical point would be 0, 0. So what I'd like to do is just go ahead and find the eigenvalues of the matrix. Oh, no. We're going to use this Maple worksheet to plot it. We're just going to find the eigenvalues and note. Are they both real? Are they distinct? Do they have the same sign or do they have opposite signs? And we're going to look at just generate the phase portion. I think we're actually Yeah, I'll send it around again. I don't know if it went all the way. Again, you can use this trick here. If these are both negative, factor out the negative. Those are going to cancel. It's just, you can do it as 2 plus lambda times 2 plus lambda. Where does it still need to go? I think it's been right on. I would just. How's this factor?
Plus 1 plus 3.
Plus 1 plus 3, yeah.
I think that's right. So, what are the values? -1, -3. So you might just note that they're real. Okay, we got 2 real values. They're not the same, they're distinct. So we got unequal values, unequal real values, both negative. Okay. So you can try and make that leap to what kind of critical point it's going to be. But let's go ahead. But let's use Maple. So again, just to give you guys how to use this, how to change some of these. You can go into almost any one you want. So let's do this one. So let's put in the dx dt, that's this guy, equals -2x plus y. So this looks pretty similar already. I'm just going to write -2 times x of t plus y of t. And the equation for y is x of t minus 2y of t. So get rid of that negative. Oh, not that. There we go. Get rid of that negative, and it was just x of t minus 2 times y of t. Okay, so that should be enough, and we had 0, 0 is a critical point, and those are the eigenvalues, -1, -3. All right, so here's what we got. Both negative, real though. So you can imagine the solutions for x and y. They'd involve an e to the -1t and an e to the -3t. Yeah? So as t goes to infinity, both x of t and y of t are going to 0. And they're doing so in some weird way. So this is a, what kind of critical point is it? It is stable.
Stable.
It is asymptotically stable because, so the different kinds of stability, there's asymptotically stable or there's center. Center stability just means you have something orbiting around a center point. So this is not that. This is an asymptotically stable critical point. And I think it is a improper node. It is stable though. Now notice when you put some of these in here, they're going to have to be captioned. And that caption might not be right. See, a stable spiral. Because I changed the equation. So whatever equation was here was a spiral. This is not a spiral. This is an improper node. They all come in and they're all tangent to a particular line. If you look at that, it's a diagonal line. But all these trajectories are tangent to the same line. Okay? And that's a characteristic of an improper node. Okay? And we'd also call it a sink, where it's an asymptotically stable center point node. Okay? All right, let's work on B together. matrix of this system in B.
1, 2, 2, 1.
So, any guesses? Unequal, opposite signs.
Like, is that what the source spits out?
A source. Saddle point. Any other guesses or agreement? Okay, let's take a look. So, all I've done is I've gone into the same one and I've changed these guys here. Those are the two differential equations. So we got derivative of x of t, so that's x prime equals x plus 2y, right? And dy dt equals 2x plus y. Okay.
Oh, there's a times next to the y of t.
Where?
Right there, to your right, okay. Down.
Just keep on passing.
Right there.
Right there.
Oh, okay, and it's just plus y of t. Okay. Okay, 2x plus y.
I don't know if that'd make it throw it good.
It would. Okay. All right, there we go. So 0, 0, right here, and it's a strange one. So look at this diagonal path here. If, for instance, the initial point put you right here, or right there, it would shoot you away from that critical point. However, any point on this diagonal, in this case, would bring you towards towards that critical point. So it's neither stable nor unstable. Well, no, that's not true. It is not stable because it's not all trajectories go in towards it. Okay, and by definition, if a critical point is not stable, it's unstable. Every single saddle point is unstable. Okay, and so these points here that don't start exactly on this diagonal, notice they'll shoot off eventually. Okay, opposite signs. Yeah. So that's a saddle point. Okay. All right, I think that gives us the gist. But I think it would be instructive if you guys went through and did, on the back side, they're not all, they are. Yeah, 0, 0 is the critical point of each of those systems.
How can you tell that? Because they all have both x.
They're all homogeneous. Yeah. So this is just x prime equals 5x minus 3y. You can write it like this: x prime minus 5x plus 3y, and I've gotten all those variable terms, equals 0. There's no constants. There's no function of t. Yeah. So this would be a homogeneous system. Mm-hmm.
What do you do?
Oh, sorry, right behind you.
For C,
Mm-hmm.
with the eigenvalues being both the same and negative, What would that correlate to?
Well, we had that in the first example.
But they're not the
Oh,
same.
oh, right, not the same. If they're both the same and negative,
That's what I was gonna ask you.
both same and negative,
Should be stable.
it's gonna be stable. I think it's gonna be, maybe a spiral node. If they're both negative, then it will be stable.
Right.
And I think it's a spiral. But that'll help answer the question. I'm gonna hand you guys this. Okay. Now, I'm not gonna ask you to memorize all the different possibilities of, real, same sign, both positive, real, both negative, real opposite signs, but, unequal, real, equal, complex.
At least you can believe.
Yeah, next one.
I think two here. Two more.
Okay. So real and equal. Look at the third one down. Oh, proper or improper node. Wait, real and equal. If they're both negative, then you're going to have it's going to be stable. If they're both negative.
I'm sure imaginary would be, yeah, I was gonna kind of make sure that they're imaginary, so it can't be the same thing.
Well, yeah, they can't be, but they both have the same. They have the same real part, obviously. A plus bi, a minus bi. They have the same real part, of course, opposite imaginary part. Okay, so this sheet, yeah. Okay, complex conjugates. That's what gives you a spiral. If they're both negative, you're going to get a stable spiral. If they're both positive, unstable spiral, going outward toward infinity. All right.
And these are all fluid, they're
Right. Now, we've been examining all those ones. The critical point was the origin on that activity. Yeah. Mm-hmm. But that's not always the case, obviously. So equilibrium points other than 0, 0. All right. So let's look at this example. Oops. Given the system below, how about dx dt equals 3 minus x minus y. And dy dt 1 minus 3x plus y. All right, so obviously, I don't like to use that word, right? But 0, 0 is not a critical point of the system. How can I tell by looking at it?
In 0 and 0, you get 3 or 1.
Right, dx dt would be 3, or dy dt would be 1 at 0, 0. So it's going somewhere. X is changing, dx dt is positive, so x is increasing at that instant, y is also increasing, so it's kind of shooting off to the right, right? Dx dt is positive, dy dt is positive, so yeah, it would give you like a tangent vector that's pointing towards into the first quadrant, so that point would be moving, it would be part of a trajectory that's not on equilibrium. Okay. So not an equilibrium point, or critical point. So let's go ahead and find what it would be. Let's find any critical points. Set both equations to 0. I'm going to rearrange it. One equation, the top equation, set it equal to 0. I can write that as x plus y equals 3. I got everything on the other side. Second equation, set that equal to 0. If I get y alone, it would be 3x minus 1. might even just do this, be quicker than enter it into your calculator, I think. X plus y equals 3, but y has to be 3x minus 1. Oops. 0, y equals 3x minus 1. That's a minus. All right. So this gives us the equation, what? 4x minus 1 equals 3. Add that one to both sides. 4x equals 4, which gives us x has to be equal to 1. So according to equation 2, y has to be equal to 3 times x minus 1. X is 1, so we get 2. All right. So our equilibrium point, 1, 2. All right. Again, just to stick with the book terminology, sometimes x star, y star. So we're getting that critical point as 1 and 2. All right, and that's obviously away from the origin. Now that method of the eigenvalues that tell us what kind of situation we're in, those are when those critical points are centered at 0, 0. Okay, here we have one that's off. But there's this nice little way we can handle this, and that's we're going to affect a linear transformation on this system. Okay, we're going to shift it. Our critical point is at 1, 2. Imagine, it's in the first quadrant there at 1, 2. We're going to shift the whole system 1 unit to the left and 2 down, and put that critical point at 0, 0. Right? All right, how are we going to do that? We just want to do a shift. I don't want to do it's going to be a linear transformation in the sense that I want to take that whole, whatever this phase portrait looks like, and I just want to move it over, left 1, down 2, so that critical point at 1, 2 will be the same critical point, but now at 0, 0. Same behavior. Okay? So we can do a shift. Well, I want to shift it 1 unit to the left. Right. X minus 1. Well, I'm going to put it at 0. We'll see. You'll see what this means, yeah. So I'm going to let u be x minus 1. So of course then when x is 1, I get u equals 0, right? And let's use v, and we're going to let v be y minus 2, so that when y is 2, v is 0. So when x and y are 1 and 2, u and v are 0, 0. Yeah? Okay, let's see what repercussions this has. Okay. When I do that, I can then solve this for x. Of course, x would just be u plus 1. There we go. There's the u plus 1, right? And v would be y would be equal to v plus 2, right? Also, and this is important, when I find the derivative, du dt, okay, differentiate both sides of this with respect to t. Du dt would just be dx dt minus 0. And so it's a linear transformation. Du dt and dx dt are the same. It's just a shift, horizontal shift. Okay. Also, same thing with v. Differentiate both sides of this with respect to t. dv dt equals dy dt minus, and the constant goes to 0. So we're just taking this system from a system in the xy plane, and we're shifting it over. Technically, we're putting it into the uv plane, but u and v just represent rigid shifts. Yeah. So we're just moving everything over. Okay. All right. So substitute that into the original. So instead of dx dt, I can write du dt, right, equals 3 minus x, but x is u plus 1, minus y. Y is v plus 2. Okay, let's go through a little bit, simplify this. It's going to be, distribute that minus, I'm going to have a minus u, minus v, and look at these constants. I'm going to have a 3 minus 1, that's 2, minus a 2, those knock out. So I get negative u minus v. dy dt can be replaced with dv dt equals 1 minus 3x, x is u plus 1, plus y, and y was v plus 2. All right, so push this negative 3 here, I'm going to have a negative 3u plus a v. And now watch these constants. I'm going to have 1 minus 3 times 1, so that's 1 minus 3, that's negative 2, plus 2, it'll knock out. Okay? So look at that. Great. So now 0 is obvious. 0, 0 is obviously a critical point of that system.
So now we need the eigenmatrix?
Mm-hmm. Translated. Now we didn't do anything fancy. We just did literally a shift, and that's called a rigid transformation. So it doesn't change the shape or the behavior around those equilibrium points. It just moves it to 0, 0, and then from there we can use the eigenvalues to characterize what type of critical point we have. Okay. So if you have your book, flip it open real fast. Page 385.